Hello, I'm Jim Stewart, and I'm here to introduce our senior capstone project. From its humble beginnings mere weeks ago, Team 34 has coalesced into modulation maniacs. We are working toward using artificial intelligence to identify a waveform. This project was presented by Tal Aragaki from General Dynamics and was inspired in part by the U.S. Army's RCO AI Challenge. The Army's stated goal was to cut through the noise and increase the speed at which electronic warfare officers can identify and react to signals on the battlefield. One of the things the Army's challenge was concerned with was classification speed once a signal was detected. As an example, there's a signal on this slide, but what is it? Without prior knowledge, one might iterate through many guesses before correctly identifying the signal as a music recording. Clearly, timely classification of detected signals is important, but what about detecting the signal in the first place? The signal detection or waveform identification is the heart of our project. On this slide, there are two plots. One is noise, and the other is an LTE signal, such as a cell phone might use. Our goal is to detect the LTE signal even in the presence of noise. Our measure of success will be how low our signal-to-noise ratio can be while maintaining a high rate of detection success. For instance, it's quite easy to identify the LTE signal as the one on the left and the noise as the one on the right, because there are only two signals present and they're separated. However, in a typical environment, there are many wireless signals from devices such as laptops and cell phones. There are also many other sources of signals present, such as radio or television broadcasts. There may be many sources of noise as well, such as motors or switches. With all of these signals mixed together in one environment, it becomes nearly impossible to detect an individual signal without knowing exactly what to look for. For instance, a radio receiver can play your favorite station because it looks only at a specific frequency. But what if we don't know in advance what we're looking for? It turns out that neural networks are very good at recognizing patterns in data. Our project is to use this feature of neural networks to detect when a signal is present. We will use sampled waveforms as the input to the neural network, and output will be a yes or a no. The neural network will either indicate there is an LTE signal present or there isn't. Before we cover the details of this, my teammate Matt Hasty is going to discuss some of the prior work in this field. Thank you for your attention.
Hello, I'm Matthew Hasty from Team 34. Today I'll be talking about prior work in the field of artificial neural networks. Donald Hebb was a mid-20th century Canadian psychologist that specialized in neuropsychology. His learning hypothesis based on unsupervised learning provided insight on how the neurons in a brain learn through pattern recognition and how this learning is strengthened through repetition. In the 1960s, Alexei Ivanenko led the team of engineers and mathematicians that developed the group method of data handling. This computer-based method of mathematical modeling was composed of groups of inductive algorithms. While this was still quite some distance from machine learning, it laid much of the groundwork for future research in the field. He would later become known as the father of deep learning. There are three learning paradigms of machine learning. The first is supervised. Supervised learning is when a neural network is trained with both an input and its matching output. The purpose of this is generally pattern recognition, and will be how we'll be training our neural networks in this project. The second is unsupervised. Unsupervised learning is when a neural network is provided with unlabeled inputs and no feedback. This will generally result in clusters of statistically similar data and can be used to find unknown patterns. The last is reinforcement. Reinforcement learning is generally used for problem solving and can be rather complicated to explain. It is beyond the scope of this project. Here we have a couple key concepts used in most neural networks. The method of backpropagation allows for errors at the output of a neural network to effectively flow backwards through the neural network and make changes to hopefully improve future iterations. The concept of max pooling is most easily explained through visual representation. As seen on the lower image to the right, it is a form of compression to decrease the amount of data that must be processed and thus reduces the computations to be performed. It is accomplished by dividing the data into a grid, reducing each section within the grid to its maximum value. Max pooling is a very effective strategy in image processing. Neural networks are being used in many applications today. While we will be focusing on signal classification, learning how to set up and train a neural network can lead to many cutting-edge and exciting fields. Here I've listed a few common criticisms with using neural nets. The most common problem associated with training neural networks has historically been the large amounts of time to train them before advances in CPU and GPU technologies over the last few decades. These advances have reduced training times from months to days or even hours. While neural networks are exceedingly effective at pattern recognition, they are not practical or accurate at performing advanced computational problems, such as the 8 queens problem or the traveling salesman problem. While convolutional neural networks are the most widely known, the list on the left does not even name all of the variants. Just deciding on which one is the best for our project is a complex trial in itself, and one which will be extensively debated over the last month of our research semester. Thank you very much. Have a great day.
Hello, I'm Albert Kalustian, and I'm going to speak with you about our project scope. In this section, we'll discuss the initial inspiration for the project, our plans to research and select which machine learning approach we'll focus our efforts on, and the hardware and software decisions we're faced with. The inspiration for this project is the Army RCO Challenge. In this challenge, users were asked to design a machine learning algorithm that could identify the modulation type of a signal given a specific signal-to-noise ratio, ranging from +10 to -10 decibels. Each user was given a limited number of training samples to achieve this goal. Our group was approached by General Dynamics with an interest in focusing on the low signal-to-noise ratio aspect of this challenge. The goal of our project is to test the limits of machine learning in signal detection, primarily to learn through experimentation precisely how much noise a neural network can detect a signal within before failing. An important aspect of this project is machine learning research and selection of an approach. Our first challenge is to decide which machine learning approach is most conducive to the constraints of this project, primarily detecting a signal despite the given noise levels. An in-depth look at the machine learning options available to us will be discussed in more detail in the next section with Ben Hunter. Upon selecting and training our chosen neural network, we will begin the process of continuously reviewing the neural network's progress and adapting our approach to improve results. A second important decision we'll make is the basic signal type we will be attempting to identify throughout the project. Unlike the Army RCO challenge, we will be focusing our efforts on identifying the presence of a single data type. At the moment, we are leaning towards an LTE signal type, which uses primarily OFDM modulation schemes. We will also use various shaped noise signals to train the neural network to differentiate between false positives. An important factor in the success of our project is the computer rig we'll use for the neural network. The number of training sessions we can perform within the given amount of time will directly correlate with how successfully our neural network will rise to the challenge. For this reason, a powerful computer that could perform more calculations and training sessions in the same amount of time will ultimately give us better results. We've been advised by General Dynamics that we should expect the bulk of the calculations to be handled by the computer's GPU. For this reason, we've considered using a virtual machine to handle some of the calculations, though we'll likely use one of our personal computers to house the neural network. We'll also incorporate scripts to facilitate unsupervised training sessions even when a human user is not present. These round-the-clock training sessions should pay off with better results. Finally, our group has chosen the MATLAB Neural Network Toolbox as the main platform to base our neural network on. Our group is all pretty comfortable and experienced with the MATLAB interface, and our research has shown that the results with MATLAB should be adequate to our purposes. This concludes the project scope section of our presentation. In the next section, Ben Hunter will discuss team capabilities and facilities.
Hello, I'm Ben Hunter, a senior electrical engineering student and team member of the AI-driven waveform recognition project put forth by General Dynamics. I will be discussing the team capabilities and facilities involved in teaching our neural network, as well as provide a conclusion. Our project involves teaching a program how to recognize an entirely new signal after teaching it with a known set of signals. In order to do this, we need a pretty deep understanding of the signal modulation types we're working with. Next, we will experiment and choose an artificial intelligence that's best suited to the task we are asking it to perform. And lastly, a cognitive engine has to be chosen to facilitate the programming. Computer power is a must. We will need ample computational resources that can run unsupervised simulations within reasonable time periods. Let's talk about modulation techniques. There are many ways to carry a signal. It can be done by manipulating amplitude, phase, frequency, or a combination. Our team has and continues to research the differing features of each technique with a focus on the modulation method used to carry LTE signal. This is mostly done by OFDM, orthogonal frequency division multiplexing. Cellular providers use this to avoid frequency selective fading. This pattern will need to be learned by our AI and be able to recognize it through noise and when compared to shaped noise. Each team member is becoming more familiar with these methods in order to make more educated changes to the neural network weights and biases that will affect how good our algorithm is at detecting whether the signal is present or not. As with modulation techniques, types of artificial intelligence are also abundant and differ dramatically in how they work. Some are more adept than others at recognizing different types of patterns. Just as our brains can approach problems in different ways, the artificial intelligence that is based on that brain does the same. Propagation, feed-forward, convolutional neural networks, and deep learning are just a few. Our team has the daunting task of wading through the wealth of information to try to decide which algorithm might be the most fruitful in finding our signal pattern in real time. Finally, we get to the brains of the operation, the engine to perform all our computations, the cognitive engine to perform the thousands upon thousands of mathematical computations involved so our machine can learn. Many programs exist for this purpose and are well suited. Caffe, Chi-Square, Keras, and TensorFlow. But we've chosen MATLAB because of familiarity of use with each team member and its wealth of toolboxes specifically aimed at neural networks and LTE signals. Though MATLAB has many tools to help with the task, the computer computational power will need to be hefty. Possible GPU farms will need to be employed. We plan to discuss this need with faculty as soon as possible. So why the need for this project? In short, our society needs it. When we lose a signal because of congestion, it's frustrating. But for corporations and military applications, it can have far greater consequences. Bandwidth needs to be used more efficiently. The aim of our team is to begin the process of using AI to find a signal out of all the noise out there and identify it. This information can then be used to identify spectrums with less congestion so it can be utilized. Research is the focus at this point. Knowledge is power, and in this case, it's vital and worthy of the time. Knowing the features of our signal and how it is being transmitted will help to refine our networks to have the greatest probability of correctly identifying the inputs as signal or noise, and even to recognize a signal through varying amounts of noise. So, what is our expectation? By semester end, we plan to have completed the research phase of our project. We will have a full understanding of LTE signal and OFDM modulation. We will also have a working knowledge of the toolboxes found in MATLAB, so we can begin simulations. We also plan to choose at least 2 neural network algorithms that we feel will give us the best possible chance of correctly learning to identify our waveform. That concludes our presentation. I, as well as Matt, Albert, and Jim, thank you for your attention.